let's see, where am I going? Notability, there we go. All right, so on this one, this should be pretty straightforward because you've done plenty of molarity calculations. You can review this in chapter 5 if you need to. All right, solution is prepared by dissolving. Let's highlight important information. 50.4 grams of sucrose, 0.332 kilograms of water with a final volume of 355. Okay, when it says final volume, it's talking about solute plus solvent. Okay, because obviously, which is equal to the solution. Because obviously the solute takes up some volume. So you can't just look at the volume of the water. I realize it doesn't give that in this question, but sometimes it might. You can't just look at the volume of the water though, because the sucrose would take up some volume too. Okay, so let's first start by writing the definition of this concentration unit. Molarity, moles of solute per liter solution. Now, you can get this from the exam equation sheet. You don't have to have it memorized, okay? So now I'm going to plug in those values. Moles of solute. Do I have that? I don't quite have that yet. I have the grams. So I'm going to first convert to moles. I'm going to do that over here on the side. 50.4 grams, and I'm going to do the molar mass to get the number of moles. So molar mass here is 12 times 12.01 plus 22 times 1.008 plus 11 times 16. So 342.296 grams. So 50.4 divided by 342.296 gives me 0.147 moles of sucrose. So now I can put that in at the top, 0.147 moles of the solute. And now I'm going to do the liters. So it's like I solved for the moles, I'm going to solve for the liters, and then I'm going to divide one by the other to give me my end answer. So solving for the liters, I'll do it just this one time, but you should know that if you have hundreds of milliliters, that's going to equate to 0.355 liters. The reason is because there's 1,000 milliliters per 1 liter. So that ends up 0.355 liters. Okay. If it was like 20 milliliters, it would be 0.02 liters. So 0.355 liters. Okay. So I solved the top, I solved the bottom, and now I'm going to divide top by bottom, 0.147 divided by 0.355 for a molarity of 0.414. Don't worry too much about the sig figs. It should be 3, but I'm not going to be grading you on that. Okay, so there's my molarity. Okay, molality, second one. We'll do this in a different color just to make sure that we're setting it off. Definition, molality is moles solute per kilogram solvent. Not kilogram solution, kilogram solvent. So just the water in this instance. So from above, I already solved the moles of the solute. So I'm just going to use that over again, 0.147 moles. And the kilograms of solvent is right there in the question, 0.332 kilograms of the solvent. So now I divide. This is often very close to the molarity, but not the exact same. And little m is the abbreviation here. Okay, so that's the molality. The reason why we need to know how to do both of these is because on Wednesday, we're going to see that there are certain calculations, certain equations that require the molarity and certain equations that require the molality. Another reason is that molality is independent of temperature. So volume actually changes with temperature because a liquid is going to expand when you heat it. And so the molarity is actually going to change ever so slightly if temperature changes. So that's one reason why we don't love to use it in all instances. Molality, on the other hand, is temperature independent. Because the number of moles and the mass don't change no matter what the temperature is. So that's one reason why we like it in certain instances. All right, next question. It's the same numbers that we're starting with, but we're going to do the mole fraction and the mass percent. Okay, so same exact numbers from above, so we may end up just reusing some of those. So go ahead and pause the video, do it on your own, come back. Use that same thing of like, use the definition of what the unit is, use the definition of mole fraction, plug in the top, plug in the bottom, divide one by the other. Okay, I'm assuming you gave this a really good attempt now. Mole fraction is moles solute over total moles, which means moles solute plus moles solvent. Okay. So in this instance, we already calculated the moles of the solute from above. If you just pull that up, 0.147. So this is nice. We did it once and we're reusing it a bunch of times. And we can plug that in here too, because that says moles solute, so 0.147. If something's written on the denominator like this, it's implying that there's parentheses. Plus moles of the solvent. So how do we get the moles of the solvent? The solvent is water, and we have the mass, so we're going to have to calculate that to give us the moles. So 0.332 kilograms to moles. So it's in kilograms. We need to first get that to grams. Then we can use the molar mass to convert. So we multiply by 1,000 to get it into grams. Then if you add up the molar mass of water, it's 18.016. Sorry about that. Per mole. So that's going to give us the moles of the water, which is the solvent in this case. 332 times 1,000 divided by 18.016. So this comes out to be, oh, that's very close to a mole. It comes out to be 18, I'm trying to see where to write this, 18 point, we'll do 4.3, I'll do 4 sig figs, moles of water. Oh, never mind. Yeah. Not close to 1 mole, close to the same as the molar mass, which is totally irrelevant. It doesn't factor into anything. So it's just coincidence. Okay. So I figured out the top. I figured out the bottom. And then I'm going to do 1 divided by the other. Please recognize that this doesn't cancel. That is not a thing. That's not how math works. You have to add the bottom. That would only be if it was multiplication. It's addition. So you have to add the bottom together and then divide the top by the bottom. So 0.147 divided by the sum of 0.147 and 18.43. Okay, so the mole fraction here is 0.0079. I'm going to give 3 sig figs, 1. And we don't give a unit to this because it's just moles over moles. Now, if you were given the mole fraction, just move this. If you were given the mole fraction and, let me fix that because I'm getting distracted. Okay, if you were given the mole fraction and asked to do something with it, then you might want to add units for yourself and say moles solute per 1 mole solution is what it really is, but we'd have to do, never mind, let's wait for an example of that. Just know that it's moles over moles, so you don't usually see a unit with fractions. With percent, it'll just say percent, but it won't actually include like grams over grams because those cancel each other out. So it would be like saying moles over moles, but those just cancel. So we don't have a unit associated with this. So this is the mole fraction for this sugar water solution. Okay, last one, mass percent. So definition, grams solute over grams solute plus grams solvent. Okay, so plugging in grams solute, 50.4 grams. And then also on the bottom, 50.4 grams plus the solvent. So that in grams, got to make sure that they're the same mass unit. You can't add kilograms and grams. So that in grams is 332 grams. You can do that as a conversion factor if you want. Just multiply by 1,000. Okay. And then that's going to be our, well, wait, hold on. That's going to be our mass fraction. If it asks for a mass fraction, because it asks for a percent, we need to multiply by 100. Okay. So 50.4 divided by 50.4 plus 332. Okay, so our mass percent is 0.132%. Pretty low percentage sugar in that water. Okay. So I'm going to say that if you are doing well with this, then class would be really short. If we were in class itself, we probably would only be able to get through like 3 of these questions, okay? But this is actually a better way of doing this, coincidentally, because if you're doing comfortably with this, you should be able to get through the rest of these in like 15 or 20 minutes, which would be our full class time. If you are struggling, it is going to take you longer. Don't think of that as like, oh, class time took an hour and 20 minutes or whatever to watch. Think of it as, thank goodness that I was able to go through all these example problems and figure them out on my own time, because that really is just like study time then, instead of thinking of it as class time. Okay? Because I am going to go through and do all these questions for that reason, since we're in a video situation where you could do it at your own pace. All right, next question. Consider, okay, so you're stopping here, working the problem, coming back and looking. Consider a 10.5% by mass. So what that means is grams over grams. Glucose solution with a density. We'll see if we need that. Calculate the molarity and the molality. Okay, so now instead of being asked to calculate the mass percent, we are actually being given a mass percent. So in the other question, we were given the amount of solute and solvent. Here, though, we're actually given a concentration unit, and we're being asked to convert from one concentration unit to another. So just to summarize, we're going from mass percent to, let's start with molarity, to molarity. Then we're also going to do mass percent to molality. So when you have a question like this, you're going to approach it pretty much the same, but there is going to be a slight variation in how you treat it. So we are first going to define what the mass percent is, and we're going to include that value now. So that value, 10.5% mass by mass. So that means it is 10.5 grams of solute, okay? And then what percent means, when we're solving for a percent, usually we do grams over grams times 100, okay? Percent means divided by 100. So 10.5%, now you could do this a little different. You could do like the fraction times 100. I find that very confusing. I think this is an easier way, so I'm going to stick to this way. If you find a way to do it or see a different video and it makes more sense, that's great. But sometimes when I show two different ways, it confuses other people. So just know there are other ways to do this, and if you do it a different way, that's fine. I'm going to do it this way. When it says percent, per means divide, cent is like century, so 100%. So 10.5% is 10.5 grams per 100 grams. Now, if you remember the definition of mass percent, it's grams of solute over grams of solute plus grams of solution. Now, I don't have each of those individual things. I know that it's I just messed that up. Let's try this again. Per grams of solvent. This total together is grams of solution because solute plus solvent is solution. So I know that there's 100 total grams of solution. So how can I break that apart and get the individual things? Well, I already know that there's 10.5 grams of solute. So I'm going to put 10.5 here, which means that the rest of the 100 grams is solvent. So that is 89.5 grams of solvent. Okay, so we've now taken the definition of mass percent and incorporated that number, the 10.5, to give us kind of the different quantities for solute and solvent. Okay, at this point, this calculation is going to be identical for the first problem as the second. So I'm going to copy and paste that down here. And what we're probably going to do, the molality in this case is going to be easiest. So we're going to do that first. But I want to show you the beginning part is going to be identical. Okay, so what we basically know now is we've got, and I'm going to rewrite this up here, but you don't necessarily have to, is that for every 100 grams of solutions, we've got 10.5 grams of glucose. We've got 100 grams of solution. And we've got 89.5 grams of solvent. Okay, that's what we figured out so far. When we do the molarity, because it incorporates volume, we're going to have to use this density. That's why I'm going to wait and do that one second. Okay, so I'm going to do molality first. So now I want to do the definition of molality. I defined mass percent and I put in the numbers. Now I'm going to define molality. Molality is moles solute per kilogram solvent. Okay, so how can I use this information that I have now figured out, which I've written up here in red, how can I use that to find the molality? Well, it's actually no different now than one of these problems that we did above. We have the grams of the glucose, so we can convert this into moles. And then we have the grams of solvent, so we can easily convert that into kilograms. Okay, so I'm going to take the 10.5 grams of glucose, C6H12O6. You can tell I'm already going to run out of room a little bit. I could put this up here because that's going to be used in the next calculation anyway. So I'll go ahead and do that. I'm going to do a molar mass of glucose, which I know is around 180, but I should calculate out what it actually is. It's 180.156. Okay, which turns out to be 0.0583 moles of glucose. Okay, so now I can put that down here, 0.0583 moles of solute. kilograms solvent, I have the grams of solvent, so all I have to do is divide by 1,000. So 0.0895 kilograms solvent. And that's it. That's going to be the molality. So I solve that out. And the molality comes out to be 0.65. All of these have 3 sig figs, I believe. 651 molal. I don't think I said that earlier. That's how we say that. When we say molarity, we say molar. When we're saying molality, we say molal. Okay? That's our answer for converting 10.5% by mass into molality. All right. It is only slightly more complicated to do the molarity. So definition of molarity, moles solute over liters solution. Okay, we already found the moles solute earlier, 0.0583 moles solute divided by liter solution. Okay, we don't have the liters of solution. We have the grams of solution. It's 100 grams of solution. But they told us the density, which converts grams to milliliters, and then we could convert that to liters. So I'm going to do this one in purple, again, just to offset things so we don't get confused as to what part is what part. So I'm going to take the 100 grams of solution. I'm going to use the density. Now I have to flip it. It's 1.03 grams per 1 mil. So I have to flip that. See, this is why all of that dimensional analysis, conversion factors that we did in the first semester is so crucial, because you just have to be very comfortable with manipulating units in order to do these calculations. So if you're struggling with that, you're going to have to set aside some time. That was supposed to be, you were supposed to have come from Chem 1 with confidence in that. All right, and then it actually needs to be in liters. So we're going to go ahead and do 1,000 milliliters per liter. Okay, so that's going to cancel out and give us the liters of the solution. So 100 divided by 1.03 times, no, sorry, divided by 1,000. Okay, so this comes out to be 0.0971. So I'm going to put that in the bottom now, 0.0971 liters. And that's going to tell me, when I divide those, that's going to tell me the molarity. 0583, 0971. So the molarity is 0.600 molar. Moving right along. So there's our molar, and this is our molal. They're always very close, molarity and molality for a given solution, but not typically, not the exact same thing. It's because density of water is 1 gram per milliliter, but you don't just have water. You have water with a solute in it. So it's going to be slightly off of 1. That's why they're very close to each other, but not the same. Okay, take a break if you need to. Ooh, that is a lot of questions. Okay, I might leave at least one for us to do together as a warm-up. All right, pause the video, move on to the next one. And we're back. What mass of sucrose is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Okay, this is a big, long question. Let's leave that before we first define what 11.5% sucrose by mass is. Okay, then we'll try to answer that question. So the circled part is the question. The 11.5% is probably going to be a conversion factor that we're going to use to get to that question. So that's a good way of thinking of it. when we did molarities, we thought of molarity as a conversion factor a lot of the times. We could use molarity to convert between a volume and moles, or moles and a volume. Or for that matter, we could go from moles to grams as well. So any concentration can be thought of as a conversion factor. It's supposed to be an I there. But we need to put that in terms of solute over solvent, or whatever the definition is. And the reason why it's a conversion factor is because it's one thing over the other. Okay, anytime you have one unit over another unit, that's a conversion factor. So let's define this first, 11.5% sucrose. So percent, again, is per 100. 11.5, and this is by mass, 11.5 grams sucrose. That's the solvent, or solute, rather, over the total solute plus solvent, which we know is going to be equal to 100 because it's percent, per 100. So 11.5 grams of the sucrose. Guess I'll rewrite it all. It's just tedious. Plus 100 minus 11.5, right? Because they have to total 100. So 88.5 grams of water. Because water is the solvent. So 100 grams solution. And I don't know yet which one of these I'm going to use, whether I'm going to use the 100 grams of solution, or whether I'm going to have to use those individual quantities, solute and solvent. Okay, so either one of these is correct on the bottom. All right. What mass of sucrose, so grams is what we're trying to get to, is contained in 355 mils, so that's what we're starting with, of the solution. Now, it doesn't really specify this. It says of a soft drink. That's the solution. We're talking about the sucrose in water. Okay, so we need to figure out, how do I get from mils of solution to grams of sucrose? I can tell you right now, we're going to use this as a conversion factor. Okay, these are all grams though. So we have to get from mils to grams first, which is why they gave us the density. So I'm going to start by going from milliliters to grams using the density. Then, and this is grams of solution to be clear. Then I want grams of sucrose, so I need to get rid of grams of solution and get to grams sucrose up here. So I actually didn't need to have this part here. I didn't need to break it down because I just need the 100 grams of solution. So all I have to do here is put in the density, 1.04 grams per 1 mil. And then I have to put in the mass percent, 11.5 grams of sucrose for 100 grams of solution. So in this instance, I did not have to break it down into solute and solvent. So again, the key point here is that I'm using the mass percent as a conversion factor. 355 times 1.04 times 11.5 divided by 100 is 42.5 grams of sucrose. So that's disgusting. That can't possibly be how much sugar is in there. No, I guess it could. I just think that's probably a high mass. So it's saying there's 42 grams of sugar in 355 mils, which is like, oh, that's probably close to like a, no, it's not even a 20 ounce. It's like 12 ounces. It's like a can of soda. That's so gross. 42 grams of sugar is a lot, in case you don't know that. All right. Next question. This one's going to be a little bit more complicated because we are going to do parts per billion. So give it a try. The next one's really easy if that helps. Okay. Hopefully you've stopped work the problem, and come back. A water sample is found to contain the pollutant chlorobenzene with a concentration of 15 parts per billion by mass. I'm going to define this before I even look at the rest of the question, okay? 15 parts per billion by mass. So 15 grams of chlorobenzene per billion grams solution. Now, it's possible that I might need to break this down into grams of chlorobenzene and grams of solvent, but realize that a billion minus 15 is basically a billion when we're talking about significant figures. So I'll write it down just for the sake of reiterating this. So this is 15 grams. This billion grams of solution is 15 grams chlorobenzene plus 10 to the 9th minus 15, which is, okay, a billion is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then minus 15 would be 9. Oh, I don't want to do this. Okay, it's basically a billion is my point. Do you get that? Because it's going to basically be 999999985. Okay, so if we only wanted 2 sig figs there, we would round that to a billion. I don't think we even need to use this here. So I'm going to leave it there, but I don't even think we'll need to use it. We're probably going to be able to rely just on this. Okay, so we've defined what 15 parts per billion by mass means. Again, per billion means 15 divided by billion. Okay, now let's get to the question. And I'm going to set it up like we always do. What volume? So equals, they don't say milliliters or liters, so I'm just going to put it as milliliters. Equals milliliters of water. That's what we're trying to get to. We're starting with 5.00 times 10 to the second. I don't know why they did that. That's just 500. Let's just write it as 500. 500 milligrams chlorobenzene. Can I just write CB? I'm tired of writing chlorobenzene. Chlorobenzene. Okay, that's where I'm starting with. I'm trying to get to milliliters of water. All right, so because this is so dilute, this is synonymous. Volume of water is going to be volume of solution. These are going to be identical because there's hardly any solute in here. Now, technically, we would want to count this as the grams of water, and then we would want to convert that to milliliters using the density conversion. It's going to be a bit of a nuisance. We might as well just round it. So let's just assume that we're talking about 1 billion grams of water for every 15 grams of chlorobenzene. Okay, or another way of thinking that, the way I would word this on the test is I would say what volume of solution instead of water. They just mean because like you took a sample of water like out of the river or something. Technically that's solution. If there's solute dissolved in there, which there always is in, any natural water source, that's a solution. So really they're taking a volume of solution. They're just saying water because a normal person thinks of getting river water as water, not as a solution. Okay, so let's just substitute in volume solution here because that's how I would write it. That enables us to use just this conversion factor and not worry about the fact that we've got this whole roundy thing with this. So that's how I'm going to simplify this question for us. Okay, so this says volume solution now. All right, so we're going to start with, which means our answer is volume solution or river water, okay? We're going to start with the milligrams of chlorobenzene. I have to convert that into grams because that's what this conversion factor is in. So 1,000 milligrams per gram. And again, these are of chlorobenzene. So to get rid of that, I need grams of chlorobenzene on top. And, oh, I can't quite go to milliliters of solution yet. So I'm going to go to grams of solution. Get a little more room. And then I'm going to go from grams of solution to milliliters solution. And that's where I'm going to use the density. Okay, so the mass percent, well, the parts per billion mass, not percent, the mass parts per billion is going to be used here. The density is going to be used there. And then this was just a metric conversion. Okay, so again, using concentration as a conversion factor. So 15 chlorobenzene for every billion solution, and then 1 gram per mil for the density. Yeah, we don't really need it because you're just multiplying by 1, but, you know, we do need to convert from grams to mils, and it's not always exactly 1. So 500 divided by 1,000 times a billion divided by 15. Of course, it didn't put it in scientific notation for me. So this is going to be 3.3 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th milliliters solution. So just for interest's sake, I'm going to put this back into liters. And there's about 4 liters in a gallon. So that is basically like 8,000 gallons. Okay, that has, what was the question? 500 milligrams. So 8,000 gallons of water is going to have that 500 milligrams of chlorobenzene. Even 8,000 gallons is hard for us to imagine. You know, a gallon of milk, 8,000 of those, that's a little bit tricky for us to imagine. But that's how much would need to be for like 500 milligrams. I mean, 500 milligrams, that's like a Tylenol pill, like a tablet of Tylenol. So it's a pretty small amount in a really big amount of water. Is it dangerous? I don't know. I don't know that much about chlorobenzene. Benzenes are generally dangerous, and you throw a halogen in there, it's probably even worse. Is it enough to be toxic? I don't know. Okay, this one's easy. This is totally chapter 5. You don't even have to have any new information. You could have done this from chapter 5. So pause, do the question, treat it as a review question. Go look up chapter 5 information if you need to, and then come back. Okay, describe how to make. Well, if we're making this solution, we're going to need to know how many grams we have to put into this 50 milliliter volumetric flask. Okay, so this is going to be 50 mils. And the description is you add that many grams, you dissolve it in a little bit of water, you know, maybe 10 mils or something. You shake it up, and then you fill up the water. So here's our grams of potassium. We mix it together with some water, and then we fill up the rest of the water to the line. So that's the description. What we really need to figure out is how many grams of that do we need to put in there. So here's our conversion factor. Here's the unit we're trying to get to. And here's the thing we're starting with. Okay, for molarity, the conversion factor is 0.08 moles of the solute, so potassium chromate in this case, per 1 liter solution. Okay, so we need to convert to liters, so 1,000 milliliters per 1 liter. Then we're going to use the molarity to get us into moles. Usually I try to put the units first, and I neglected to do that. And then it wants it in grams because we would weigh that out in grams, you know, in a lab setting. We wouldn't weigh it in moles. So we're going to need the molar mass too. So molarity is used here. Molar mass is used here. Everything's going to cancel to give us grams of potassium chromate. Okay, so 0.08 moles per liter, and then potassium chromate. I'm just going to Google this one. Is 194.1896 per 1 mole. I need a few minutes, babe. Okay. I'm recording my class. Okay, so when I calculate that out, this comes out to be let's see how many sig figs, just 2 here. So 0.78 grams. Okay, that one's super easy. What do we got? 2 more? These are both actually really easy too. So all 3 of these last ones are just from Chapter 5 review. We should have done those first. These are the only ones that are new. Okay, so I probably won't even talk through these solutions. I'm just going to post the answer and you guys can look at it. I'll work through it because I might as well just finish the recording. But, you know, I'm probably not going to talk you through it too much. Okay, so in this one, let's actually do the second one first. This is a dilution problem. So you are using M1 V1 equals M2 V2. So this is your 1, and it's a little bit more complicated than that. Because you're solving for M2, but then you're going to do something else with it. Okay, we'll still do it first. It's fine. So M1, 5.50 molar, V1, 42.5 mils. M2 is what we're solving for. Now, the reason I knew that is because it was asking something about a certain number of grams. You know, we don't have grams in this, so I know molarity is the only thing I don't know, okay? So I'm going to calculate, let's see, this new volume. Gosh, I have to scrap this whole problem. I got a little distracted. In case you didn't hear, there was a kid that came in and asked a question. So I have to scrap this whole problem and start over. It's more complicated than I thought initially. Let's just do this one first. Okay, you have 0.459 molar, has a total volume of 252, and it's left on the counter. 45 mils of it evaporates. I feel like we did this question last semester, but whatever. So now the new solution is 270 milliliters. So V2 is 207 because it evaporated. This is a very straightforward dilution equation. It's actually an evaporation in this instance because V2 is less than V1. But I think this is good to do first before that other one because that other one is more complicated. I wish that other one was more simple, but we're going to go with it, I think. All right, 252 mils. M2 is what we're solving for. It evaporated and now is 207 mils. So the new molarity is 0.55. Let's see, and we'll leave it at 2 sig figs. So 5, 6 molar. Okay? All right. The reason why this question is confusing, I'm going to leave it for next time because I need to go help this kiddo. We've done plenty today. So I'm going to leave this for our start. And I swear it's not just because it's confusing, but I might even simplify it for our warm-up. But I'm going to leave this for our warm-up. Okay? Have a great day, and I will see you guys on Wednesday.